Researchers at the Pacific Northwest National Laboratory have found a new element in critical infrastructure protection. They've discovered how the algorithms that rank pages in Internet searches can also help planners better understand how to prevent cascading failures in places like electrical or water systems. Here with how it all works, PNNL mathematician Bill Kay. Dr. Kay, good to have you with us.
Hey, good to be here, Tom. When you imagine ranking websites by importance, the same sort of mechanism goes into determining what is important about infrastructure assets when you consider the system as a whole, the grid where things are linked up.
In other words, you're looking at dependencies from what I've read. That is to say, this water pump is not the biggest part of the infrastructure, but it could have a lot of effect on things downstream of it, for example, should it get jammed.
Yeah, absolutely. A power plant gives power to a water treatment plant, gives water to a hospital, right? And if the power plant fails, then the water plant can fail. And if the water plant fails, then the hospital can't provide water to patients.
All right, so we have critical infrastructure, let's say the electrical grid, and cascading is a problem that we know from history has caused widespread failures. One thing leads to another, and next thing you know, too much current is cascading down on something that can't handle it, and then there's a blackout. I lived through a couple of them. I really remember the blackouts. And what is the database of the dependencies that you have to evaluate in the first place? Because in Internet searches, there's activity that has created a history that gives importance rankings to the algorithm. How do you establish that in, say, a chain of critical infrastructure components?
The work that we did used one particular data set that was the all hazards analysis data set, was curated by domain experts. And so this is the kind of thing where we wanted to demonstrate that our method was a good way to stop cascading failures in a network. But this is the kind of thing where maybe domain experts would come to us and say, we have a network, we've written down the dependencies, and we are concerned about what cascading failures spreading throughout this network could do. Can you tell us which are the most important things to stop from failing?
So they know, therefore, what their dependencies are. What is the element they don't know then? If they know the dependencies, shouldn't they say, well, this is what absolutely can't fail? In other words, it sounds like there's a ranking here missing.
The place that this kind of came from was Google's search algorithm called PageRank, right? And once upon a time, websites were ranked highly if a lot of other web pages pointed to them just directly with hyperlinks. And people figured this out, and what they did was they spun up a bunch of fake web pages that didn't say anything to link to their web page to artificially inflate the ranking. And so what Google said was a web page shouldn't just have a bunch of links to it. It should have a bunch of web pages that themselves are important point to it. And those things are important because lots of things point to them. And so you can't just look at one asset and say, what are the things that point at it? It needs to depend on a lot of things that are themselves important. And those things need to depend on a lot of things that are themselves important. So Google's algorithm takes a holistic view of the entire network structure and ranks the web pages like based on how important they are in the whole system rather than based on a local thing.
We're speaking with Bill Kay. He's a mathematician with the Pacific Northwest National Laboratory. And did you have Google's cooperation in this investigation? Because that algorithm is kind of an important asset for them.
Oh, yeah. There are implementations of PageRank in a lot of scientific computing things. So it is not a guarded secret. I mean, probably the nuts and bolts of how Google's internal algorithm actually works is theirs, but how PageRank works is just a linear algebra thing. It's got a Wikipedia page. It has implementation.
So it's almost an open source type of thing.
Yeah, absolutely. Yeah.
And just to be clear, you used the more recent holistic version of the algorithm and not the original sheer PageRank based on links version.
That's correct. Yeah.
All right. And well, give us an example of how this might work. I mean, I'm a critical infrastructure operator. I want to know what's important, what thing I absolutely don't let fail. What's my process? What's presented to me to be able to effectuate that?
It's less that you are operating one infrastructure unit and more, let's say you're in charge of distributing resources to defend infrastructure and you've got, let's say, your budget limited or time limited or something, and you can protect 5% of infrastructure assets to stop them from failing. What we can do is look at the dependency network and say which things are the most likely to get caught up in a cascading failure. So if something random fails and the failure is spreading, this thing is likely to get hit. And also, if this thing fails, the failure will cascade the farthest. And so what we said was we can rank all of the infrastructures in say a power grid or something like this. Say, if you're budget limited, let's grab these top 5% and make sure that they have backups or something like that.
You can take almost what they would call a risk management approach to it.
Exactly.
And do you think this works in other than physical infrastructure domains? For example, the banking system, where, cascading failures or real estate, that type of thing.
PageRank has been used to analyze a number of different network constructions, but one thing that we did that was, I think, somewhat novel is that we actually cared about both things getting caught up in the cascade and how far they magnify the cascade going forward. I looked and I haven't found anything that has considered both of those simultaneously. And so I think the part of the novelty of this work is that we care about getting caught and spreading a failure.
Sure. And just briefly, tell us a little bit about yourself. You are a mathematician. Where'd you come from, and how did you end up at PNNL?
Yeah, that's right. So I'm actually a pure mathematician by training. I got my PhD at Emory University in Atlanta, and the field that I studied it's called graph theory, but if you asked people in the applied space, it would be called network science. And I was sort of headed towards academia and took a different track and wound up at a lab, and I get to work on these really cool applied graph theory problems that hopefully can be impactful and helpful to keep things working.
By the way, is the chalkboard still a useful tool in the pursuit of mathematics?
Yeah, I got one on my wall. I've got a chalkboard and Hagoromo chalk, the fancy Japanese chalk. I don't know if you've heard about this.
Not personally, no.
Yeah, okay, yeah. Mathematicians love it. Doesn't squeak, doesn't get dust all over you. You don't get the white lung.
All right. Well, if I ever need a blackboard, I'll try it. Dr. Bill Kaye is a mathematician with the Pacific Northwest National Laboratory. Thanks so much for joining me.
Yeah, thank you.
And we'll post this interview along with a link to more information at federalnewsnetwork.com/Federal Drive. Subscribe to the Federal Drive wherever you get your podcasts.